For this exercise, let us compute nabla A xb in polar coordinates, where xb are the components of the position vector. Note that in polar coordinates, the position vector is given by ρ times e ρ, which means that x ρ is equal to ρ and x phi is equal to 0. Since what we want to compute has two indices that can each take the values ρ or phi, let us start by computing nabla ρ x ρ. By definition, this is equal to the derivative in the ρ direction of the component x ρ, which is equal to ρ, plus gamma ρ a ρ x a. If we perform the derivative, it is equal to 1, and since the only non-zero component of x is the ρ component, the second term becomes gamma ρ ρ ρ multiplied by ρ. And since this Christoffel symbol is equal to 0, the result is equal to 1. For nabla ρ x phi, the definition gives us d ρ acting on 0 plus gamma ρ a phi x a. And here the first term vanishes and we are left with gamma ρ phi times ρ, which is equal to 0 because the Christoffel symbol is equal to 0. Continuing with nabla phi x ρ, this is equal to d phi acting on ρ plus gamma phi ρ times ρ. And here both terms are equal to 0, the first because ρ does not depend on phi, and the second because the Christoffel symbol is 0. Finally, for nabla phi x phi, this is equal to d phi acting on 0 plus gamma phi ρ phi times ρ. And here the first term is 0, and the Christoffel symbol in the second term is 1 over ρ, and we therefore find that this is equal to 1. Note that this is exactly in line with the partial derivative in the a direction of the position vector being equal to the tangent vector basis. In particular, the derivative in the ρ direction of the position vector should be equal to nabla ρ xa multiplied by ea. If we write out the sum over a, this is nabla ρ x ρ times e ρ plus nabla ρ x phi multiplied by e phi. Inserting the results from above, we find that this is equal to e ρ, which is also what it should be because this is the definition of e ρ. Doing the same thing for d phi acting on the position vector and going through the corresponding computations, we find that this is equal to e phi, which is again compatible with the definition of e phi as the partial derivative in the phi direction of the position vector.